Hi everyone, this is lesson 2-4, Zeros of Polynomial Functions. This is video 2.4.3 and 2.4.4. And our learning objective for today will be for students to be able to solve polynomial equations and use the upper and lower bound test to find an interval in which all real zeros exist. Alright, so we're going to first start talking about solving polynomial equations. This is a typo right here. This should say equations, not functions. And in this example, the water level in a bucket sitting on a patio can be modeled by f of x equals x cubed plus 4x squared minus 2x plus 7, where f of x is the height of the water in millimeters and x is the time in days. So just to reiterate what they've given us for information, x is the time measured in days, and y or f of x is the height of the water in millimeters, and mm is the abbreviation for millimeters. On what day or days will the water reach a height of 10 millimeters? So what we're going to do here is we have a function given to us, f of x, that models the height of the water based on time and days. And so what I'm going to do is it's giving us a height of 10 millimeters, and they want to know how long it's going to take for the water to reach that height of 10 millimeters. So I'm going to substitute 10 for y, or f of x, and then I get x cubed plus 4x squared minus 2x plus 7. Now, another way we can solve this is by moving the 10 over to the other side. So I get to move that 10 over by subtracting 10, which leaves me with then 0 on this side, on the left side, and on the right side I would get x cubed plus 4x squared minus 2x minus 3. Now what I'm looking at here is a polynomial function set equal to 0. Now this isn't my answer. What I need to do is find the zeros of this polynomial function, of this cubic function. Again, because we have our 0 here, right here. We have our 0 right here, and this polynomial function over here is a cubic function, and so what we're going to do is we're going to apply some of the other theorems that we've talked about with finding the zeros of polynomials on the next slide. So, what do we know about this polynomial function? First of all, it's a cubic function. Its degree is 3, which means that it has at most 3 zeros. There's a possibility of having 3 zeros. We also have what's called the rational zero theorem, in which case we can take the factors of p and the factors of q, p being my constant, q being my lead coefficient, and we could make a list of the rational zeros. So I know that our rational zeros are the factors of p, which are plus or minus 1 and plus or minus 3. And the factors of q, because our lead coefficient is 1, is just plus or minus 1. Now, to find the rational zeros, I divide every p by every q. So I could divide plus or minus 1 by plus or minus 1, meaning I could divide positive 1 by positive 1, positive 1 by negative 1. I could divide negative 1 by positive 1, or negative 1 by negative 1. So that's when I take this particular p-value, plus or minus 1, and divide it by plus or minus 1. And if I take plus or minus 3 and divide it by plus or minus 1, I get 3 over 1, negative 3 over 1, 3 over negative 1, and negative 3 over negative 1. So that gives me possibilities. If I look at these right here, 1 divided by 1 really is just positive 1. 1 divided by negative 1 is negative 1. Negative 1 divided by positive 1 is also negative 1. And negative 1 divided by negative 1 is just positive 1. So all 4 of these end up just giving me either positive 1 or negative 1. And on the bottom here, if I divide all these numbers, I end up just getting either a positive 3 or a negative 3. So those are the possible rational zeros of this polynomial equation. Now, in order to determine which of these 4 are actually zeros to this polynomial equation, since my list isn't all that long, I'm going to use synthetic division on the next slide to test whether or not 1, negative 1, 3, and negative 3 are zeros of this polynomial function. Alright, so I'm going to start by testing 1 and negative 1 to see if they're actually zeros of the polynomial. Again, these were our coefficients of our polynomial, 1, 4, negative 2, and negative 3. And when I carry out synthetic division using a 0 of positive 1, I carry down the 1 here, multiply this 1 by this divisor of 1. 1 times 1 is positive 1. When I add my columns, 4 times 1 is 5. Now I'm going to take the 5 right here, and I'm going to multiply it by my divisor right here. 5 times 1 is positive 5. When I add the column here, 5 and negative 2 give me a positive 3. And when I multiply the 3 by the divisor up here of 1, I end up with a positive 3. When I add my column here, I get a 0. So I right now know that x equals 1 is one of the solutions to this polynomial equation. Again, this was a typo. And I'm going to go ahead and see if we have more solutions, because remember at the very beginning we decided that the cubic function could have, since it was a degree 3 polynomial, it could have up to 3 zeros. So I'm going to go ahead and look to see if there's any more zeros for this polynomial function. I carry down the 1. Again, I'm going to multiply this 1 by negative 1, which is my divisor. I get negative 1. When I add this column, I get positive 3. When I multiply positive 3 by negative 1, I get negative 3. When I add this column, I get negative 5. And when I multiply negative 5 times a negative 1, I end up with a positive 5 here. And I add my last column, and I get a remainder of 2. So I know since my remainder is not equal to 0, that negative 1, x equals negative 1, is not a 0. Again, the reason why I said x equals 1 is a 0 is because this remainder here was equal to 0 when I carried out the synthetic division. Now I'm going to check the other 2 rational zeros that we came up with on the last slide, which is 3 and negative 3. So I'll start by testing 3, which is 1, 4, negative 2, negative 3 were my coefficients. If I carry out synthetic division, again, carry down the 1. 1 times 3 is 3. 4 plus 3 is 7. 7 here times 3 is 21. 21 minus 2 is 19. 19 times 3 is 57. And I end up with a remainder of 54. So again, x equals 3 is not a 0 of the function because 54 is my remainder and not 0. And the last number I'm going to check is negative 3. If I have my coefficients again, 1, 4, negative 2, negative 3, and I carry out my synthetic division, start by carrying down the 1. 1 times my divisor is -3. 4 plus -3 is a 1. 1 times -3 gives me -3. I get -5 here when I add -2 and -3. And -5 times a -3 gives me +15. And when I add that to -3, I get 12. So -3 is not a zero of the function because we get a remainder of 12 and not a remainder of 0. So all our rational zeros are tested. The only one that actually ended up being a 0 to the function is x equals 1. So that means that the solution to our question how long is it going to take for the water to reach 10 millimeters, the answer to that is 1 day. Because again, at the very first slide, x was measured in time, in the number of days, and y was measured in the height of y was measuring the height of the water in millimeters. Alright, it's time for you to check your understanding. In this example, the path of a ball is given by the function f of x, and the function is given to us. It's a quadratic function, a quadratic polynomial, because our degree is 2. The highest exponent is 2. Where x is measured in time in seconds, and f of x is the height above the ground in meters. After how many seconds will the ball reach a height of 25 meters? So we have 4 choices, A, B, C, and D. Why don't you go ahead and solve this polynomial function, or polynomial equation rather, and select your answer. And when you're done, press submit. Alright, so we're going to go ahead and solve this polynomial equation together. First of all, we know that the y-coordinate they give us, the height is 25 meters. So I'm going to substitute that for f of x because f of x, again, is the height above the ground in meters. So I'm going to substitute 25 for f of x, which is equal to -4.9 x squared plus 21.5x plus 40. And I am going to go ahead and find the zeros of this polynomial. In order to set it equal to 0, I'm going to subtract 25 from both sides, which gives me 0 equals -4.9 x squared plus 21.5x plus 15. Now, what you have here is this quadratic function, and we have many different ways we can solve a quadratic: factoring, graphing, and quadratic formula. And given the fact that my coefficients are so awkward because they're decimals and not whole numbers or integers, I think I'm going to go ahead and use a quadratic formula on the next slide to solve this polynomial equation rather. Okay, so here is our polynomial, and again, it's a quadratic, and so I know that this is my a value. This should have an x attached to it. This is my b value, and then my constant is c. And in order to solve this, I'm going to use the quadratic formula, which you guys learned about last year, and we also discussed at the beginning of the school year. Okay, so we're going to a reminder here of what the quadratic formula looks like. It's x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And what I'm going to do is make sure that a lot of people made mistakes and they were plugging in variables for a, b, and c. What you want is a is only this coefficient, b is only the coefficient of x, and c is just your constant. You do not use the x variable inside the quadratic formula. So if I am going to take the opposite of b, we get -21.5 plus or minus the square root of 21.5 squared minus 4 times -4.9 times 15 all over 2 times negative 4.9. And what we're going to look at then is simplifying underneath our square root. And I'm going to first start out by multiplying 21.5 by itself. That gives me, when I square 21.5, I get 462.25 minus. Now I'm going to multiply all three of these numbers together for negative 4.9 and 15. That gives me a product of 294. It's actually negative 294. So with this minus sign in front and the fact that these three numbers multiply to give me negative 294, this is going to be plus 294. And then we're going to divide by 2 times negative 4.9, which is negative 9.8. Now we need to continue simplifying, and I'm running out of room here, so I'm going to move to the next slide. Alright, so continuing on from the previous slide, we have negative 21.5 plus or minus the square root of 756.5 divided by negative 9.8. And when I square root 756.5, I get approximately 27.5. So I'm going to add plus or minus 27.5 divided by negative 9.8. And if I continue by taking negative 21.5 plus 27.5 divided by negative 9.8, and my other solution is going to be negative 21.5 minus 27.5 divided by negative 9.8. Now if I carry out these operations, when I add negative 21.5 and 27.5 and divide by negative 9.8, I get negative 0.612. And when I add negative 21.5 and negative 27.5 and then divide by negative 9.8, I get a positive 5. Now, remember x is a measurement of time, and this first response here is negative, and time cannot be negative. The lowest value time can take on is 0. So I know this is an extraneous solution, which leaves me with my only valid response as being x equals 5. That means that the correct answer was D. Now, just so you know, we could have taken that original polynomial function that was set equal to 0, and we could have graphed and found the zeros. We also could have tried factoring it. It's probably not likely factorable, but those are just some methods that you can use when solving a quadratic equation. Alright, so we are going to be talking about upper and lower bound tests in the second half of our lesson. And the upper and lower bound tests are used to determine a window or an interval in which all our zeros of our polynomial function exist. I know that's a mouthful, but we're going to try to look through this key concept here, and then we'll work through some examples together. Now it says, let f be a polynomial function of degree n greater than or equal to 1. So linear, quadratic, cubic. Linear has a degree of 1. Quadratic has a degree of 2 or an n value of 2. Cubic would have an n value or degree value of 3, etc. Then degree of 4 is a quartic function. Our coefficients, the numbers in front of our variables, have to be real, and it has to have a positive leading coefficient. And it says, suppose f of x is divided by x minus c using synthetic division. So we're going to use synthetic division and not long division in this upper and lower bound test. One thing is if C is less than or equal to 0, meaning your divisor in synthetic division is less than or equal to 0, and every number in the last line of the division is alternately non-negative and non-positive, then C is a lower bound for the real zeros of the function. So what we're looking at here is when we carry out the synthetic division, what pattern we are looking for is that the last line of our division is alternating between non-negative numbers and non-positive numbers. And the reason why they don't just say positive and negative is because you can include 0 as being a non-negative number, and 0 is also a non-positive number because 0 is neutral. So you can kind of use 0 as like a, how do I say this, leeway. You can count it as a non-negative if you need it to be non-negative, and you can use it as a non-positive if you need it to be a non-positive. And so if that occurs in the last line of your division, then C is a lower bound for the real zeros of the function, only if, again, your numbers in the last line alternate back and forth between non-negatives and non-positives. Now, if C is greater than or equal to 0, so your divisor is greater than or equal to 0, and every number in the last line of the division is non-negative. Again, non-negative includes 0, so it could be 0 or any positive number. The word non-negative means not negative. Then C, the divisor, is an upper bound for the real zeros of F. Now we'll discuss this concept of lower bound and upper bound some more in the examples. So what do we have here? An upper and a lower bound test for this polynomial function f of x, and it says determine an interval in which all real zeros of f of x must lie. Explain your reasoning using the upper and lower bound test, then find all the real zeros. So first of all, this polynomial function f of x we know has a possibility of having 4 zeros, because my degree is equal to 4, so that means that we have 4 possible zeros. Doesn't mean it actually has 4 zeros, it's just a possibility. And we need to figure out an interval. Again, an interval is like what we use to describe a domain. So an interval is going to be what it's going to say is all of our real zeros lie in between this x value and this x value. So what you're looking for is you're going to have a bracket and a bracket, and this right here is going to be your lower bound, and this right here is going to be your upper bound. And what you're saying is that all the zeros, all the real zeros of this polynomial function of f of x are in this interval or domain. Okay, so I hope that makes sense. And we're going to explain your reasoning using the upper lower bound test that we've described, those patterns. Again, the lower bound test, your divisor has to be less than 0, and for your upper bound it has to be greater than 0. Now, in the previous slide it said less than or equal to 0 for the lower bound and greater than or equal to 0 for your upper bound. However, we're never going to use 0 as our divisor because we all know that, or we should know by now, that we cannot divide by 0. So, what we're going to do is we're going to look at this polynomial function, f of x, and I'm going to look at what its rational zeros could be. And again, the rational zeros come from the constant, which is negative 12 rather, and that's my p-value. And so the factors of p, all the numbers that go into negative 12, or negative 12 is divisible by, are negative 1, 1, 2, negative 2, 3 and negative 3, 4 and negative 4, 6 and negative 6, and 12 and negative 12. And the factors of Q, which is the factors of my lead coefficient, which are 1 and negative 1, are easy to find just because the only numbers that 1 is divisible by are 1 in itself. So my rational zeros then are found by taking P and dividing it by Q, all the factors of P, all these numbers right here, divided by either 1 or negative 1. Well, the nice thing is that if I divide all these P values by either 1 or by negative 1, I just get that same exact list. And that's a rather large list of zeros to be checking using synthetic division. It would take you like 4 pages of paper. So what I want you to do is, it just gives me an idea here. If I look at my negative zeros, okay, so a negative 1, negative 2, negative 3, negative 4, and negative 12. Okay, if I look at those values, I'm trying to pick out of those which could be a possible lower bound, again, because we want the least x value that we can use so that we can view all the real zeros of our polynomial function. So here's what I'm going to do. I'm not going to go through and test all of these. I'm going to kind of use I don't want to say a cheater way, but a shortcut. By graphing this polynomial function f of x and looking at the graph to help guide me in determining where my upper and lower bound might be. I could use synthetic division and kind of test all of these rational zeros, or possible rational zeros in this list that I've generated, but again, there's so many of them that I don't want to spend all that time doing that, when I can just graph the polynomial function and use that as my guide. Okay, so on the last slide, I said that we were going to look at the graph of this polynomial function. And it looks like my smallest actual zero is maybe like negative 0.75 or negative 0.8. I didn't exactly find what the actual zero was because that's not the point of the question. The question is asking me to find a lower bound. And so, since my zero is just greater than negative 1, I'm going to test negative 1 first to see if negative 1 is an appropriate lower bound for this function. So using synthetic division, again, I'm going to use these coefficients in our function f of x. Our coefficients are 1, negative 4, negative 11, negative 4, and negative 12. And if I carry out synthetic division, I start by carrying down the 1, and again, I'm going to multiply this one by negative 1. That gives me negative 1. And if I add this column, I get negative 5. And what we're looking for, just as a reminder, in the lower bound, we want these numbers at the bottom here, these numbers here, to be alternating between non-positive and non-negative. Meaning that 0 is neutral and we can kind of count 0 as either a non-negative or a non-positive. And so far, it looks like my numbers are rotating or alternating between non-negative and non-positive, because here 1 is positive and negative 5 is obviously negative. So I'm going to carry out the synthetic division further, and I multiply negative 5 times negative 1, which gives me a positive 5. And when I add this column here, I end up with negative 6. So I can stop right there. I already know right at this point that this negative 1 here is not my lower bound, because I have two negatives side by side. And again, for the lower bound, you want those numbers to alternate between positive, non-positive, and non-negative. So what I'm going to do is I'm going to move to the next negative integer, I'm going to go to -2. And if I test -2, I am going to have 1, -4, -11, -4, and -12, the same coefficients of that polynomial function, f of x. And if I carry out synthetic division here, I get 1. 1 times -2 gives me -2. Add this column, I get -6. -6 right here times -2 is going to give me a 12. And when I add this column, 12 and -11 give me a +1. So far it's looking good. This is non-negative, this is non-positive, this is non-negative, and I want to make sure that pattern continues. Now what I'm going to do is I'm going to multiply 1 and -2. So when I multiply this one by -2, I get -2. Add my column, I get -6. That's great, because I needed a non-positive there. And when I multiply -6 by -2, we get +12, which is 0. Now you might look at the end and say, okay, well, 0 is neither positive or negative. It can be concluded, it can be used as either a non-negative or a non-positive. So therefore, however, if I conclude that this is my lower bound, what happens is this 0 right here is at -2. And if I start my window at -2, again, our goal is to find an interval in which all real zeros of the function lie. And if I started my interval at -2, like on my graphing calculator, if my window starts at -2, my window is going to be like right here, and that 0, we're never really going to see that 0 because it's going to be right on the edge of the viewing window. So what I want to do here is I actually have to increase, even though I think this could be my lower bound because it meets the rule, if this last number is 0, then what happens is you decrease this by 1 more integer. Now, so I guess what I'm really saying to summarize is you cannot have a lower bound that is a 0 of the function. So if that happens to you and you get a 0 as a remainder, you decrease the number by 1. And so in this case, I know that x equals -3 is going to be my lower bound. Now what I'm going to do here is this 0 right here is at approximately 6. The same thing is going to happen is when I go to test for my upper bound, I don't want to use a 0. I don't want either my lower bound or an upper bound to land on the 0 of the function. So when I, on the next slide, go to test for my upper bound, I'm not going to start testing at 6. Rather, I'm going to start testing at one integer bigger than that, which is going to be at 7. Alright, so when I test for my upper bound here, just a reminder from the upper bound and lower bound theorem, for the upper bound, I want this bottom row to be all non-negative. These numbers all have to be non-negative, meaning they can't be negative. And the other thing we're looking for is we don't want this remainder to equal 0 because we don't want our upper or our lower bound to land on the 0 of a function. So I'm going to start carrying out synthetic division. I carry down the 1. If I multiply the 1 times the 7, I get +7. When I add this column, I get 3. When I multiply 3 by 7, I get 21. And when I add this column, I get 10. And when I multiply 10 times 7, I get 70. And 70 minus 4 is 66. And when I multiply 66 times 7, 66 times 7 is going to give me 462. So if I get 462 here and I add that with negative 12, that gives me a remainder of 450. And if you look at all these numbers in this last row, they are all non-negative, which means that 7 is our upper bound. And since our lower bound was negative 3, again, lower bound comes first in our interval, and our upper bound comes second, what that tells me is that if I use this viewing window for x, so in other words, on my graphing calculator, if I used x min at negative 3 and I used x max at positive 7, you would have a window that's wide enough. Okay, here's your viewing window. Your window would be wide enough here from, here's the x-axis and y-axis. The width here on the x-axis would be wide enough so that you could view all the zeros of your polynomial function. And when I say all the zeros, I mean all the real zeros of the polynomial function. Now, one thing we have not done is, yes, we found the upper and lower bound. However, it said also list all the real zeros of the function, and those were at negative 2 and at positive 6. And I knew that because they were on the graph from Desmos. Okay, I looked at those and I just tapped on Desmos to determine the zeros. Now I could go verify that these are zeros by using synthetic division and looking for a remainder of 0 to confirm that actually x equals negative 2 and x equals 6 are zeros of that polynomial function. Alright, so it's time to check your understanding. We're going to determine an interval in which all real zeros of f of x must lie, and then find all the real zeros. Now, there's some typos here. 1 and 2, so part A is correct. I'm going to add something to this, though. I'm going to add negative 2.5 here and negative 0.58. I'm going to add negative 2.5, negative 0.58, and 3.414 here. And I'm going to add at the bottom 3.414 as my possible 0, or my actual 0 to the polynomial function. So go ahead here and work out the problem, and when you're done, obviously these intervals here represent your upper and lower bound for the polynomial function, and then after the semicolon are a list, or is a list, of all the zeros that exist on the function, all the real zeros of the polynomial function. So go ahead, work it out, pause the video, and press submit when you're done. Alright, so here's what I'm going to do. I'm going to use a little bit of shortcut here, and I only say that is because I'm looking at this p-value and at this q-value, and there are a lot of factors of negative 10, and there's 4 factors of 2. And I'm not going to test all these, but here's the deal. If I have factors of p, that gives me 1, negative 1, 2, 5, negative 5, sorry I missed a negative 2, and 10, and negative 10. I probably should put the negative 2 back here with the positive 2. It doesn't really matter, but I'm just picky and want everything kind of grouped together. Here I have factors of q, and the factors of q are 1, negative 1, 2, and negative 2. And if I divide all the factors of p by all the factors of q, they give me my possible rational zeros, which are 1, negative 1, 2, negative 2, 5, negative 5, 10, and negative 10, because I divided all these numbers of p by 1 or negative 1. And then I can add to that list by dividing all the values of p by either 2 or negative 2, which gives me 1/2, negative 1/2, 5 halves, and negative 5 halves. And if I'm looking at this list, there's no way that I am going to go ahead and test all of these to figure out where my zeros of my polynomial are. So I'm going to kind of use a shortcut and go ahead and graph this polynomial function on Desmos and look for where the zeros are, because then that gives me a good idea of a starting point for testing my lower and upper bounds. Alright, so looking at the graph of our polynomial function on Desmos, I can see that negative 2.5 is a 0, 0.586, which is actually not a rational number. We have x equals 1 and 3.4. So here are the zeros that I'm going to focus on. I know that my lower bound has to be less than negative 2.5. So the first number that I'm going to test using synthetic division is negative 3, because that's the first integer less than negative 2.5. And if I write out my coefficients of this quartic equation, it's quartic because it's a degree 4 polynomial, I have 2, negative 5, negative 13, 26, and negative 10. And if I carry out synthetic division, what I want to happen is I want alternating non-negative and non-positive numbers. So I'll carry down the 2. 2 times negative 3 is negative 6. Add the column, I get negative 11. Negative 11 times negative 3 is positive 33. And 33 plus negative 13 is 20. 20 times negative 3 is negative 60. Negative 60 plus 26 gives me negative 34. And if I multiply negative 34 times 3, that gives me a positive 102. And if I add 102 and negative 10, I get 92. So, if you look at the bottom, it alternates between non-negative and non-positive because I have a non-negative here, a non-positive number here, non-negative, non-positive, and non-negative. So I already know that negative 3 is my lower bound. Now I have to test for my upper bound, and since right here on the graph, my highest zero is at 3.4, I know that my upper bound has to be greater than 3.4. 3.414, I guess, if I use all the decimals. So the first number I'm going to test for my upper bound is the first integer greater than 3.4, which is positive 4. And when I carry out synthetic division, I want to make sure that these bottom numbers are all non-negative. So using the coefficients from my polynomial once more, I get 2, negative 5, negative 13, 26, and negative 10. And when I carry out synthetic division, so far I have all non-negative numbers at the bottom. Carry down the 2. 2 times 4 is 8. 8 plus negative 5 is 3. 3 times 4 is 12. Uh-oh. Negative 13 plus 12 is negative 1. Okay, that's no good. I know that 4 is now not my upper bound. And what I'm going to do then, if I pick a number and it doesn't work and it's not my upper bound or my lower bound, then I just keep decreasing the number from my lower bound, or in the case of my upper bound, I just keep increasing my divisor until I reach an integer that does give me the pattern I'm looking for, in this case, all non-negatives. So I'm just going to do something here and change this to a 5. And if I multiply, I carry down the 2. 2 times 5 is going to give me a 10 here, 10 plus a negative 5 is going to give me a 5 here, and 5 times 5 is going to give me a 25 here. And when I add 25 and negative 13, that gives me a positive 12. And 12 times 5 is 60. 60 plus 26 is 86. And 86 times 5, if I just work that out over here, 86 times 5 is 30, carry the 3. 8 times 5 is 40, plus 3 is 43. So 430, and if I subtract 10, I get 420. So 430 minus 10, or 430 plus negative 10, gives me 420. These are all non-negative numbers, so that means 5 is my upper bound. Now, to write out my window, though, I get negative 3, comma 5, or to write out my interval, that's negative 3 and comma 5. And the zeros, the real zeros of this polynomial function, are given by the graph up here. So, we have 4 real zeros, which makes sense because we have a degree 4 polynomial. And one of our zeros is at x equals negative 2.5. We have 2 zeros right here. One at x equals 0.586 and another one at x equals 1 right here. And our other 0 is at x equals 3.414. So we have 4 zeros, 4 real zeros in this interval from negative 3 to 5. So that if I set my window on my graphing calculator with an x min at negative 3 and an x max at 5, we would be able to view all 4 of these zeros. All right, we're done. Time to start the formative assessment.